Hello, and welcome to Conquering the Mountain, an in-depth look into how I hacked and translated Aconcagua, the infamously tricky-to-hack PlayStation game. The process of translating the game has a few steps. First, we have to identify all the text and graphics data that's in the game that we want to translate. After we have identified it, we have to program an extractor that can take those files and put it into a form that we can edit with our own tools. For example, images need to be turned into PNGs that we can open in Photoshop. And then, after that step, we have to program an injector to convert our edited files back into the game formats. For example, taking that PNG and turning it back into a binary file that the game recognizes. After we have that, we need to make sure that we're updating all of the file directories that the game is looking at to keep track of where the files are, and then rebuild the game disk. So where do we even start? Well, a good place to start is to just look at the files that are on the disk. If we put the actual disk into our disk drive on our computer, we can see what shows up. Here we have Aconcagua is a 2-disc game, so there's disk 1 and disk 2. From our previous experience with PlayStation games, we have a pretty good idea of what some of these files are. We know that these folders at the top contain some audio and video files, but with a hidden secret that we'll find out later. This A01 file is for identifying what disk number it is, so 1 for disk 1 and 2 for disk 2. This dummy file is basically just an empty file that helps the CD push its data to where it's most efficient. It helps with the actual disk reader to read the disk, but otherwise it's completely empty. This PROGRAM.BIN is, well, we don't know. Binary files or .bins can be literally anything, so we don't know quite yet right now. But we do know that it's identical in disk 2. This SCPS file is a PlayStation executable. It contains basically the first bit of code that runs when the disk is first booted up. These sound files are audio tracks, as you could probably guess, and this system.conf just contains some boot up information. Wait, what were we looking for again? Text and graphics? Wait, where's the text and graphics? Well, we've ruled out everywhere else. Everything that we're looking for must be in this program.bin file. So let's take a close look at program.bin. If we open it up in a hex editor, we can see that it's made up of many units, and each unit starts just like this. This is a standard header for a PlayStation overlay. Each unit has a specific size and a location that's going to be loaded into memory. It's located right here, and here, from our previous experience, we know how to read these files pretty well. But what about the rest of it? After that part at the top, the header, it's mostly unintelligible gibberish that looks like this. There's nothing that we can make sense of, except a little bit. You can notice a few words here and there if you look closely. But otherwise, it doesn't really help us. This is not really a format, and we can't edit it. But why is it like this? It's like this because the file is compressed. So file compression, I've talked about it at much more length in my Racing Lagoon deep dive video, but basically it saves a lot of space on the disk, and it increases loading times. The specific compression algorithm used here is, once again, Lempel-Ziv-Stor-Zemansky. Once again, you can learn all about it on my Racing Lagoon video. We can get the actual uncompression algorithm by, once again, using a disassembly of the game or stepping through a debug emulator. But after we've uncompressed it, you can see that it has much more of a normal structure. We can make out many more words. It's something that we can work with now. Now, something that we notice when looking through these files is that there are certain files inside of each of these units. Each unit is actually a package containing many, many files. In fact, every single scene in the game has its own package that contains code, textures, models, audio, basically everything. And this means that some textures, for example, the main character's texture, is repeated maybe up to 100 times. Why is the game structured like this? Well, I'll let Sony's lead system architect, Mark Cerny, explain how this is actually a technique that they use to increase loading times on disk-based mediums.
The difficulty being that hard drives are neither particularly fast nor flexible. If all your data is in one block, which is frankly not very likely, you can load 50 to 100 megabytes a second, depending on where the data is located on the hard drive. Let's assume it's on the outer edge, which means loading a gigabyte takes 10 seconds. If you compress your game packages, you can fit more data on the Blu-ray disc and also effectively boost your hard drive read speed by the compression ratio. We support zlib decompression on PlayStation 4 that gets you something like 50% more data on the disk and 50% higher effective read speed. Unfortunately, though, it's highly likely that your data is scattered around in various files on the hard drive, as well as sourced from multiple locations within those files. So lots of seeks are needed at 2 to 50-ish milliseconds each. My rule of thumb is that the hard drive is spending 2/3 of its time seeking and only 1/3 of its time actually loading data. Putting all of that together, a gigabyte is very roughly 20 seconds to load from a hard drive. Now, a gigabyte, back to the hard drive. Another strategy for increasing effective read speed is to make big sequential chunks of data. For example, we might group all the data together for each city block. That removes most of the seeks, and the streaming gets faster. But there's a downside too, which is that frequently used data is included in many chunks and therefore is on the hard drive many, many times. Marvel's Spider-Man uses this strategy, and though it works very well for increasing the streaming speed, there's a massive duplication as a result. Some of the objects like mailboxes or news racks are on the hard drive 400 times. What I'm describing here...
So what Mark described there was the bundling of data into a single package so that it could be loaded all at once without the disk having to do a seek being when the disk has to move to a different location. By packaging all the data together, all of the data for a single scene can be read in one continuous stream, eliminating seeks. And this is what games on the PlayStation 4 did, and it's what games on the PlayStation 1 did as well. It was only until the PlayStation 5 in which it was using a solid-state drive instead of a disk drive that we were finally able to eliminate seek times, and this technique of bundling data is no longer necessary. Because the data is duplicated in so many different places, I had to write a propagation tool that for every single file that I modified, it would need to be propagated to every single instance of that file. So back to the game. What is it that we're actually looking for? Well, the game has 4 different methods of displaying text. One, it has these menus that appear when you first load up the game. 2, it has its normal dialogue that appears during gameplay. 3, it has the subtitles that appear during cutscenes, voiced cutscenes. And 4th, it has the text that appears during its full motion videos. All 4 of these instances of text are completely unique and different from each other. Let's start with the menu text. Well, this one turned out to be the easiest. The text in the menus turned out to be stored as TIM images. TIM is a standard format for the PlayStation 1, and tools that already exist for editing, extracting, modifying, basically doing everything with them. These were no problem at all. One thing to keep in mind when you're editing graphics on classic hardware is color palettes. We're not actually able to use whatever colors we want when we're editing an image. We have to use the colors that were already being used in the image. Photoshop has a tool that allows you to import and save color palettes, and that's what you have to use when you're editing these images. Number 2, we have gameplay dialogue. If we scan through the files that we've decompressed, we can spot the text just by scrolling through it in a hex editor, because it turned out that the text in this game was using a very standard format. It was using Shift-JIS. You can see the text here as it appears. Editing it turned out to be not too much of a problem because of this. Now, one thing that's different from Racing Lagoon is that Aconcagua uses text pointers. Basically, every single line of text has its own entry in a pointer table. The pointer table stores the address, the memory address of each and every single line. When we're editing the lines, we also need to make sure that we're editing the associated pointer table entry for that line. But let's talk about the font that the game uses. While the game does have a pretty nice looking English font, it does have some errors that we want to fix. Considering that this game features a lot of Spanish voice and text, it's actually missing some of the characters that are necessary for writing Spanish. First, we need to find that font, though. By looking through the files with a graphics editing tool, a raw graphics editing tool, we can find the font. It turned out that it was right here. But there's a problem. As you can see, it seems like each character is stacked upon other characters, and it doesn't seem quite obvious how we can separate them out. This is what's known as a multi-channel image. Each individual image is stored with others across multiple bit planes. Well, what does that mean? So the game was storing 1 bit per pixel images inside of a 4 bit per pixel container. What this means is there are 4 images stacked on top of each other. The first uses the first and 5th bits of each byte. The second image uses the second and 6th bits of each byte. The third using the third and 7th, and so on. And it repeats in this pattern. We can separate all 4 images by using this knowledge. And if we do that, we get this. This is the font as it existed in the shipping game, and after doing some edits to it, this is what it looked like. As you can see, it has some errors, such as this upside down question mark that's used in Spanish is actually pointing the wrong direction. Number 3, we have the cutscene subtitles, and this is where things go off the rails. At some point when I was working on this project, a programmer actually approached me and said that they were never actually able to figure the subtitles out. And it's because they are very, very strange. They are not standard at all. So far, it's been pretty easy. We've dealt with pretty standard formats, but this is where things get really weird. So because these images used a rather high color depth, they used quite a few shades of gray, I was certain that each subtitle was actually a distinct image. I couldn't find any font that the game was using to pull these characters from. And I could not find these images anywhere in these files. It wasn't in PROGRAM.BIN, which to our knowledge was supposed to hold everything. Through the process of elimination, I discovered that it had to have been inside the audio files. Because they were being stored in the audio files, these subtitle images are actually being streamed in while the associated voice clip was playing. You see, the audio files are stored in an STR format that has this very specific structure. The file is divided into sectors, and between every audio sector are 7 non-audio sectors that the game usually uses for FMV video. But here it was doing something quite a bit different. The game can use these sectors for anything it wants. Channel 1 is reserved for audio. As we can see, this pattern repeats every 8 sectors, with channel 1 being for audio. But everything in between there can be used for anything. So what the game was actually doing was compressing the subtitle, splitting that subtitle into tiny fragments, and then dispersing those fragments over the audio clip, the total audio clip. The number of fragments that it was splitting into was arbitrary. The locations of the fragments were basically arbitrary. The location of the fragment within the sector was also arbitrary. It was extremely, extremely strange how the game was storing these. But in the end, it did allow them to save memory, because it didn't need to have every subtitle loaded into memory at once, because it was streaming each one in as it was being played. So I understood how it worked, but how could I actually extract a format that's so strange? Remember, when I said that the locations of the fragments were arbitrary, that makes it very difficult to extract them correctly. Well, what the game was doing was assembling all the fragments itself at runtime. So what I could do was play the game in an emulator with the memory viewer open and copy manually every single compressed subtitle into a file as it appeared in the cutscene. This was a very, very manual process that I did have some help with from Mr. Nobody, but it was quite tedious, but necessary, because the format was just so strange. But we're still not done there. After uncompressing and editing the files, how could I re-inject it back into the game? That's another problem to solve. Well, I wrote a program to determine the maximum length of each fragment that it could be and how many times it's duplicated, and compare it with the original image so that I could then do a find and replace on each and every single fragment of each and every single subtitle inside of the audio file. This was an alright solution. It still had some mistakes when it wouldn't match up the correct chunk or the correct fragment to the right place, but I could correct those mistakes manually by looking at the logs. It was pretty easy to figure out when something was not in the correct pattern. But this method has some issues. Since I was only editing the data, I couldn't edit the metadata of the subtitle. For example, what the dimensions are, what the subtitle's width and height are. And I couldn't use any more storage space than the original compressed image. Storage space being how many actual bytes the image was taken up. This is a major problem, because English is a much more verbose language than Japanese. Meaning, to get the same point across, you need more characters. For example, the word washing machine uses 15 characters to write out in English, but only 3 in Japanese. How could I solve these issues? Well, problem 1, the dimensions of the image. Well, I could use just a slightly smaller font and resize it when necessary. This isn't an ideal solution, but it's the one I had to go with. At times when you're playing this game, you might notice a word missing here or there. I tried to keep the subtitles as sensible as that I possibly could to make people who are hard of hearing still be able to enjoy the game. And at sometimes you might notice the font suddenly shrink for a single line. It's not the ideal solution, but I think in the end I was able to create an acceptable experience. But problem number 2 is more interesting. I couldn't take up any more storage space for the compressed images than the original. How could I improve the size of the file. Well, I could use a font that has a better compression ratio and uses fewer colors. Well, what does that mean? The images were being compressed using run length encoding. Again, in my Racing Lagoon video, I go over this compression method in depth. But basically, the way to improve your compression ratio when the files are being compressed with run length encoding is to reduce the amount of edges that the compressor sees. The way the compressor works is it'll start in the top left and go to the right on every single row. It'll do the first row, and then the second row, and then the third row of pixels, and so on and so forth. If we look at just this first line of pixels at the very top of this image, we can see this right here. An image will compress better if it has fewer stripes on this band. Fewer stripes. What that means is, to get a better compression ratio, I have to use a font that looks blockier. And this is the one that I found. It's quite blocky, as you can see. But that gave it actually a better compression ratio. Also, by only using black and white and not gray, I was able to improve the compression ratio as well. So that brings us to full motion video, the FMVs that play at the very start and end of the game. Normally, this would be easy. There are tools for subtitling PlayStation 1 videos already, but there's a problem. None of them worked on this game, and I couldn't understand why. Let's take a look on Google. Well, this is what I found. There is one person who has worked on the FMVs of Aconcagua and tried to extract them. That person is M35, someone who has created a very, very powerful tool for editing PlayStation 1 videos. What I found here in the first file that I looked at from his code is ASCII art of Jackie Chan doing his signature pose here where he's very, very confused. That's not a good sign. Basically, instead of using the standard video formats of the PlayStation 1, the developers of Aconcagua decided to write their own from scratch, and it's a complete mess. You can pause the video and read through his comments, M35's comments on the FMVs. It's very, very strange. But this was a huge problem. There was no program in the world that could let us edit these videos. Reading through his code some more, you could even see an explicit comment saying that he was not going to support Aconcagua's videos. M35 might genuinely be the only person in the world who could help me with these videos. What the hell was I going to do? Well, I was going to ask him nicely and hope for the best. Well, it went pretty well. You can see, here's the actual email that I sent him, and the first thing he says is, this is an email he hoped he would never see. But he promised that if this project reached completion and the only thing left was the videos, that he would create an encoder for it. Well, that came to actually pass. At the end of the project's lifespan, I did reach out to him, and he did create, very graciously, I might add, I'm very thankful that he did this, an encoder for Aconcagua. After I had the encoder, it was as simple as writing a subtitling program, because the way the extractor encoder works for the videos was actually, you export every single frame of the video to a PNG, and then we can edit those PNGs and then inject it back into a video with the script that I had written. And that was what it took. After that, we had all 4 of the puzzle pieces put together, and the game was 100% fully translated from top to bottom. Thanks so much for watching this video, and I hope to see you in the next one.